So, chapter 22, part 2, we left off here in the last part. So for successful cross-aldol condensations, you can use one that doesn't have any alpha protons and one that does, so that you can know which one will serve as the nucleophile and which one will serve as the electrophile. In this case, this will have an alpha proton to deprotonate under basic conditions, so this will attack the electrophilic carbon center. And then under base and dehydration of water, you're going to get the alpha beta unsaturated aldehyde in this case. Same thing here. This one doesn't have any alpha proteins. This one does. As a result, this one is the one that's your nucleophile. As a result, that's going to attack, and then you're going to generate the aldol, form the alpha beta unsaturated aldehyde. So here's a problem 3. Propose a mechanism for the base catalyzed aldol condensation of acetone. Here's acetone. You're going to deprotonate the alpha hydrogen. Electrons will go there. Then you have your enolate ion, in which you can have resonance structures as shown over here. That enolate ion will then attack your electrophilic carbon center. Electrons will go out to the oxygen, and then this will protonate, generating the aldol. You can do aldol cyclization, in which you deprotonate right at your alpha carbon, having that lone pair of electrons go attack intramolecularly, so that electrons go to the oxygen, and then this gets protonated, and then in the presence of base, this will dehydrate to form the alpha beta unsaturated cyclopentenone. So intramolecular aldol reactions of diketones are often used for making 5- and 6-membered rings. Rings smaller or larger than 5 or 6 members rings are not favored due to ring entropy. So if we look at aldol condensation and we do a retrosynthetic analysis, here's your aldol that exists. This could possibly come from, right, this is your alpha, this is your beta connection. This would be your benzaldehyde, this will be your propionate. Here, in the case when it's unsaturated, again, this is where the connection is made. So this came from acetophenone, and this half came from this acetophenone. Claisen ester condensation, so you can do condensations with esters as well, in which you have one of the esters deprotonate, being a nucleophile, attack, electrons go to the oxygen, come back down and kick off the alkoxide, forming that beta ketoester. Important thing to note is that the Claisen condensation occurs by nucleophilic acyl substitution, with different forms of the ester acting as both the nucleophile, the enolate, and the electrophile, the ester carbonate. In Dykman condensation, you have, right, your diethyl adipate or 1,6 diester. This is in a possible 5-membered ring for intramolecular cyclization. So under basic conditions, you protonate the alpha hydrogen, and then you have your electrons come, attack to the oxygen, and then once it attacks the oxygen, the electrons from the oxygen come back down, and then this gets kicked off, right, forming the cyclic beta ketoester. Same thing, now here's a 6-membered ring for that you can possibly see, in which now you have deprotonation, right, at your alpha carbon, and now you have your electrons will attack, electrons go to the oxygen, and then go back, and then kick off at the methoxide, generating the cyclic beta ketoester. Cross Claisens, you can take two different esters, but one ester should have no alpha hydrogens, and these are examples of no alpha hydrogen based esters, so these will be useful. And then ketones may also react with an ester to form beta diketones. Cross Claisen, so here's one with no alpha hydrogens, here's one with. As a result, this gets deprotonated, and then this will become nucleophilic and then attack. Electrons will come up, electrons come down, and this gets kicked off, forming the ethyl benzoyl acetate. So the ester without the alpha hydrogens serves as the electric component. Cross-Claisen condensations with ketones and esters. So if you have ketone versus ester, ketone is more acidic. As a result, ketone is more likely to deprotonate and serve as an enolate versus the ester, as you can see here. And so if we look at the cross-Claisen mechanism, here's your ketone that's more acidic. It's been deprotonated, attack, oxygen electrons go out, then oxygen electrons come back down and kick off the OR, generating the acylated ketone. So here's another problem. Propose a mechanism for the self-condensation of ethyl acetate to give ethyl acetoacetate. So here's ethyl acetate. It's going to deprotonate the alpha carbon, generating your enolate. Once it generates your enolate, it'll then nucleophilically attack the electrophilic carbon center. Electrons will go to the oxygen. Oxygen electrons come back down, kick off the ethoxide, and generating the ethyl acetoacetate. Once the ethyl acetoacetate is generated, then another equivalence of the ethoxide will deprotonate. Electrons will go there, and then this will react, right? And will protonate to form ethyl acetoacetate if there's nothing else in the system as an electrophile. Show what ester, this is another problem, would undergo Claisen condensation to give the following beta ketoester. So as you can see, this is the alpha carbon, right? And so you're adding to this ester this guy, right? And so that's formed via Claisen. So then you see these are the two that will react with one another. So here's two. Two of these will react in the presence of base. Deprotonate. One will deprotonate, right? This will then serve as a nucleophile attack. Electrons come up, come down. Remove the ethoxide, generating the product. In your book, Table 22-1 gives you all the conjugate acids and bases and shows you that having actually diketone moiety really brings it to more acidic than just a single, which is important. And then it shows you what the relative pKa's are for water, methanol, and ethanol. Malonic ester. So this is a malonic ester. In the presence of base, it'll deprotonate right here, and then this will serve nucleophilic. And actually, you can do, instead of adding protonated water, you can do SN2 and substitute and add the R group right here. And then when you add, right here, and then when you add protonated water and heat, you can have decarboxylation occurring and generating your substituted acetic acid. So in order to show the mechanism, it's easiest if you draw out your malonic ester in a ring form, so that you can then easily say, okay, electrons from this form the double bond. This is your CO2, breaks off, forming a double bond here, and these will pick up that hydrogen. And this will generate CO2 and the enol, and then it will tautomerize to generate the substituted acetic acid. So here's an example of the malonic synthesis. Here's a malonic ester shown here. This is going to be the temporary ester group that will decarboxylate. So if you do ethoxide to deprotonate right over here, then react with alkyl halide. This will then react here to form the new bond. And then if you add acid, heat, water, this will decarboxylate to form the substituted acetic acid. Now you can envision that you can undergo another substitution, so you can take that alkyl malonic ester, right, and then you can react it with sodium ethoxide, alkyl halide. This will then undergo another addition, and then under heat and acid and water, this will decarboxylate. So malonic ester synthesis goes through alkylation of an enolate, hydrolysis, and decarboxylation. To design synthesis, you want to look at the product and see what groups are added to the acetic acid. Use those groups to alkylate malonic ester and then hydrolyze and decarbonize. So here's a problem. Show how malonic ester synthesis is used to prepare 2-benzyl butanoic acid. So here is it shown. So there's one substitution and another substitution, and this will come from the malonic ester. And so if you start off with malonic ester, sodium methoxide, phenyl bromide. This will then add this, right? That's the first addition, and then you can do a second equivalence of the sodium methoxide, this time with ethyl bromide, and this will add the other group. Then when you want ready to decarboxylate, you add acid, heat, and water, and will decarbonate. Acetic acid synthesis. So here's ethyl acetoacetate. In the presence of ethoxide, alkyl bromide, this will add. Then when you add water and heat, only this side will decarboxylate, right? So it's similar to that malonic ester synthesis, but the final products ends up being ketones because this side is does not have an ester. So we can look at alkylation of acetic ester. Here's your non-ester part and here's your ester part. So this is the part that's going to decarboxylate under basic conditions. You have, right, deprotonation of the alpha carbon, nucleophilic attack, X leaves, and then you have this alkyl acetic ester. Then the alkyl acetoester or beta ketoester under acid, heat, and water will form the carboxylic acid, which is a beta keto acid, and this decarboxylates to generate the substituted acetone. So an acetoacetic ester synthesis goes through alkylation of the enolate, hydrolysis, and decarboxylation. To design a synthesis, you want to look at the product and see what groups are added to the acetone. Use those groups to alkylate the acetoacetic ester and then hydrolyze and decarboxylate. So here's another problem. Show how acetoacetic ester synthesis is used to make 3-propyl-hex-5-ene-2-one, shown here. So these two groups are being added, and this is the acetone. So in your synthesis, here is your acetoacetic ester. You're going to deprotonate with ethoxide, add your alkyl halide. Here's one addition. Again, deprotonate, add your other alkyl halide. Here's your second addition. And now when you're ready to remove this, you can add heat and water, and under acidic conditions, this will convert the ester into the acid and then decarboxylate, forming that. You can do what are called Michael additions. So if we look at an alpha beta unsaturated compound, you can see that electrons can move, right, under resonance, and you have charge separation here as well as this moving again, and where carbocations here. And so you have two possible positions over here and over here, right, that you can add to. And so if we look at that, that's either 1,2 addition or 1,4 addition. So when the attack occurs at the carbonyl group, protonation of the oxygen leads to a 1,2 addition. So here's your attack, protonation of the alcohol, this is 1,2. You can then also add or attack at the beta position, in which electrons will shuffle along and then protonate. So this becomes a 1,4 addition. This will tautomerize to form to the keto product. Donors and acceptors. Here are examples of donors, and here are examples of Michael acceptors. This is in your book, table 22-2, and so you can look at these and just make sure you understand what a donor is. Specifically, donors will have source of electrons. Acceptors here are shown here. 1,4 addition of an enolate to methyl vinyl ketone, or MVK. So here's your malonic ester enolate. This will add. Here's your MVK. This will move. So it's a 1,4 addition, right? And then electrons will come down. This will protonate to form your 1,4 product. So an enolate will do a 1,4 attack on alpha beta unsaturated ketones or methyl vinyl ketones. And so here's a problem 8. Show how the following diketone might be synthesized using Michael addition. So if we look at this, we have to look at the alpha beta. So here, this is where you can see the addition, because Michael addition's 1,4 here. And so this could be split into these two parts, where here's your nucleophile, here's your acceptor. And then you can move forward in that direction. The other type of reaction is called Robinson annulation. Here you have your ketone, and here's your methyl vinyl ketone. So this is going to add, right, deprotonate and then add, and then form this new cyclohexenone under basic conditions. In terms of mechanism of the Robinson mechanism, you can start off at deprotonating, deprotonating that hydrogen, making it nucleophilic. Then you'll have addition at the 4 position, electrons moving, and then your oxygen electrons will come back down, protonate, forming that delta diketone. And then you have another equivalence of the hydroxide, deprotonate, forming this nucleophilic. And then this will attack the electrophilic carbon center, electrons to the oxygen, and then it gets protonated to form this 6-membered ring, right? And then you have the dehydration. This will remove that proton, and then electrons will go here and then move, form a double bond, and remove the OH. So in general, you can usually spot a product of a Robinson annulation because it has a new cyclohexanone ring. The mechanism is not difficult if you remember. Michael goes first, followed by aldol with dehydration. So this ends chapter 22, part 2.